Hi, and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion of various topics related to forces and Newton's laws and their applications. Today, we are focusing on the forces of friction. Now, I said that plurally because, as we will see, there are more than one type of friction, and they apply in different circumstances. At this point, you should basically recall sort of what Newton's laws say about forces. Specifically, if you have an object which is at equilibrium, then the sum of forces must be zero. And this basically means that the object is either at rest and remains at rest, or it is moving with a uniform velocity. Specifically, we're interested here in at rest and remaining at rest. The second of Newton's laws, this was Newton's first law, the second of Newton's laws says that when you do not have equilibrium, when the forces are not all balanced, the net force, or the total force, is the mass times the acceleration. So this is forces not balanced. The third law we're less interested with in today's video. It's important, but it's not really what we're focused on this time around. Okay, let's consider these two laws, and now let's consider a case of a heavy object sitting on a surface. So I've got this surface, I've got this maybe large crate or safe or something like that that is sitting on the surface, and maybe I try to push the crate. So I apply some force in this direction to the crate. And the crate, of course, does not move because it is very, very large and heavy. Where does this other force come from? So if the crate doesn't move, then that means that we're looking at this law right here, and so the sum of forces must be zero. Now I can draw a couple other forces on this crate. For example, I know that there is some gravity, so I could draw a gravity force, and I could draw a normal force. But I notice that gravity and normal force in this particular drawing would be vertically oriented, and the force I'm applying is horizontally oriented. The implication is that there must be some other force present in the horizontal direction opposite the direction that I am pushing. This must be a friction force. Okay? So friction is what prevents this large object from moving. The fact that the object is very large means that even without friction it may not move with very much acceleration, but we need another force like friction to prevent it from moving at all. Now let's consider another case. Let's consider a case where we have the large object, or even a not so large object, but let's use our same large object just for the fun of it. And initially it's moving forward with some velocity. Let's put that in green. So initially we have a velocity v initial in this direction. As it slides along the surface, it slows down. So as it slides, it slows. What does that imply? Well, by Newton's second law, the sum of forces must be mass times acceleration. And again, I can draw gravity, mg, and I can draw a normal force here, force normal, and neither one of those is in the horizontal direction. A is horizontally oriented, meaning it's slowing down or it has an acceleration to the left. And that means that I need to have a net force, an unbalanced force, to the left. So force net acts to the left. And in order for that to occur, once again, we have to have some force here that's not shown in this drawing acting to the left. And that force again is friction. Now there's a third thing that we can observe about this scenario versus this scenario. I've labeled the force in both cases friction, but I will find that if I push very, very hard on this, the object doesn't move, and if I push very weakly, the object doesn't move either. In other words, this force of friction in this case changes based on how hard I'm pushing on this object. Okay? In this case, the friction force more or less is constant, assuming that the surfaces are identical. Assuming that this surface right here is identical to itself everywhere, assuming that this bottom surface of this remains the same everywhere, that there's no like scraping off or sanding down or something like that as it moves, then this will be a constant deceleration. So we might say in this case, friction here is more or less constant, whereas friction here varies depending on the force that I apply. Okay, that would be this force F. Okay, so that's one observation. The other observation is that I can push on this object a lot harder, or somewhat harder, and therefore friction in this case can become somewhat larger than is indicated by the object slowing down. So if we call this one case 1 and we call this one case 2, then friction in case 1 at maximum is greater than friction in case 2. So that means that we may have two types of friction operating here. And those two types of friction we call static and kinetic. So this last statement that I made here could, with these two things, be considered as force of friction static max is greater than force of friction kinetic, which is more or less constant. Okay. Now, what is it that actually determines the amount of friction present? For this, you'd have to do a variety of essentially experiments. So, for example, you could do an experiment in which you swap out what kind of material this large object is made out of. Or maybe just swap out what material the bottom of the large object is made out of. Similarly, you could swap out what the surface that it's sliding along is made out of. You'll find that friction depends upon both of those surfaces. You'll also find that if you make the object larger, that friction increases. If you make it smaller, friction decreases. You'll find that if you make the object larger or smaller like that, you can make the object more massive or less massive, or you can simply change its volume. That if all you've done is change the volume or the contact area, but not the mass, not the weight, and not the normal force, that friction will not change. Okay, so friction doesn't depend on those things, but it does somehow depend on mass, weight, and or normal force. And so now the question becomes, how do you sort of distinguish between those three factors? After all, if you increase the mass of an object, its weight should also increase, as should its normal force. So you'd have to basically do some experiment to distinguish between those three. For example, if you get on an elevator and you move upward or move downward, and you accelerate upward or accelerate downward, then the mass of the object remains the same, but the normal force and the apparent weight should both change. Okay? And you'll find that on those elevators, the amount of friction for that object changes given the same object and same surface. So, okay, it's not mass, it must be either weight or normal force. How do we distinguish between those? You'll recall in our previous video that I discussed what happens when you put an object on an inclined plane or ramp at angle theta. That, among other things, if the object is put on this inclined ramp or plane, or this inclined plane or ramp, that the result is the normal force changes to be perpendicular to the ramp, and also changes in such a way that its magnitude is somewhat less than gravity. The normal force ends up being m times g times the cosine of the angle. So this lets us separate between the weight of the object, or the force of gravity on the object, and the normal force. And what we find is that in this special case, that friction depends on normal force, not on weight. So let's write that down. Friction depends on normal force, not necessarily weight or mass. We would find the same effect, by the way, if we were to put the object against a wall, let's say. So the object is here, and we go ahead and press on it so that the normal force opposes our pressing. The amount of friction present will depend upon how much normal force we apply, or the maximum friction present depends on how much normal force we apply, and therefore we can change how big or small the object is and yet keep the friction more or less the same by changing how hard we press on the object. Now, with that said, if we want the object to remain in place, we do have to press hard enough that the friction force overcomes gravity. The equation, therefore, which relates friction to normal force, F friction static, just is that it must be less than or equal to some maximum amount that's determined by the coefficient of static friction and the normal force. And for kinetic friction, force of friction kinetic, the F sub little f k, is equal to mu sub k times F sub n. So those are your equations that sort of get how much friction should be present. And that statement that the maximum value of the static must be greater than the kinetic tells us that mu static is greater than mu kinetic. Now, this coefficient, or these coefficients of friction, must be either determined or, more usually in a problem's case, either given to you or looked up in a table of values. So they have different values depending upon the value of the two materials, the object and the surface it's on. So that's all for today. Thanks for watching.